Okay, what's up guys? So today we're going to be looking at the photoelectric effect. And on the photoelectric effect, the first thing that we have to actually understand is the electromagnetic radiation and the electromagnetic spectrum. So as you can see here, I do have my electromagnetic spectrum and my visible spectrum of the electromagnetic spectrum. I want you to pay particular attention to the frequency here. See, the frequency actually increases from the radio waves to the gamma rays radiation. And on the other hand, if you look at the top here, we have our wavelength, which is indicated by lambda. And that wavelength actually increases as we move from the right, which is the gamma rays, to the left, where we have our radio waves. In other words, it's actually the opposite of the frequency. As the frequency increases from the left to the right, the wavelength actually decreases from the left to the right. Now, on the other hand, we must speak of the energy. Since the frequency actually increases from the radio waves to the gamma rays, we expect the energy also to increase from the radio waves to the gamma rays radiation. And this can be confirmed by the equation where we calculate the energy of the photons in the radiation, which is energy of a photon is equal to the Planck's constant times the frequency. And this equation actually is telling us that the energy of a photon in a given type of radiation is directly proportional to the frequency of that radiation. So in other words, we're simply saying that as the frequency increases from the left to the right, from radio waves to the gamma rays, so does the energy. The energy also increases from the radio waves to the gamma rays. In other words, the gamma rays have got the highest energy while the radio waves have got the lowest energy. In other words, here we're saying E is going to be the lowest here, and then E is going to be the highest this side. And all this is as a result of the fact that the frequency increases as we move from the radio waves to the gamma rays. Another equation that can actually explain this, but in terms of the wavelength, is the energy of a photon being equal to hc over the wavelength, where these are constant. H is the Planck's constant and c is the speed of light in a vacuum, so divided by the wavelength. So as you can see, the energy is inversely proportional to the wavelength. In other words, E will be inversely proportional to lambda, and this tells us that as the wavelength decreases from the radio waves to the gamma rays, the energy actually will be increasing. So this is something that we should take note of when we are going to be looking at some of our calculations and trying to understand the photoelectric effect. Now let's move on to the visible part of the spectrum. On the visible part of the spectrum, we can see as we move from the left to the right here that we actually have a red, orange, yellow, green, blue, indigo, and violet arranged in order of their wavelength and frequency, whereby the frequency actually also increases from red to violet. And just like in the full electromagnetic spectrum, the longest wavelength will be in the red light, which will have the lowest energy, and the highest energy will be in the violet, which have the shortest wavelength and the highest frequency. So this is something that we should keep in mind when we are studying the photoelectric effect. Okay, so it's actually important for you to remember the arrangement of this radiation, and to actually remember this, you just need to remember the first letter of the type of the radiation, and you can expand from there. So it's going to be, for the radio waves, the first letter is R. For the microwave, it's M, and then I, V, U, X, and then G. So you can chunk this up so that it'd be easier to remember into R, M, I, and then Vox, and then G. So you can see this would be much more easier to remember rather than remembering all this information. And you can actually expand this where R represents the radio waves, M the microwave, I the infrared, V the visible, and then U the ultraviolet, X-rays, G gamma rays. And in this mnemonic device, obviously, that would mean that as we move from the left to the right, our frequency will be increasing. So in other words, as we move from left to right, the frequency increases and the wavelength decreases and the energy actually increases. So this is all you need to know about the electromagnetic spectrum. And then now let's move on to the visible part of the spectrum. So we can also do the same thing that we did with this, and here this will be R, O, Y, G, and then B, I, V. Right, so you can separate this like this. This will be Roy G Bev for red, orange, just like that. And obviously this the same from left to right, the frequency will be increasing and the wavelength decreasing, and then the energy will be increasing. So you can see the frequency will increase, energy will also increase, and then the wavelength will actually be decreasing from left to right. This is very important, and that's what we really need to know in as far as the electromagnetic radiation is concerned, and also the fact that electromagnetic radiation actually is transmission of energy. In other words, electromagnetic radiation contains energy that we shall see and discuss as photons, which is what we're going to be dealing with later. Now, there is also another thing that you need to know in as far as the speed of light is concerned, or the speed of the electromagnetic radiation is concerned in the vacuum. So if you want to calculate the speed of light in a vacuum, you should use this equation here. The speed of light in a vacuum actually depends on the frequency and the wavelength. And as you can see here, the speed of a light in a vacuum will be equal to the product of the frequency and the wavelength. And this is actually a constant which is equal to 3 times 10 to the power of 8 meters per second. So that will be the speed of light in a vacuum. And then, of course, like I said, this is also a constant, which is the Planck's constant. And the Planck's constant is equal to 6.63 times 10 to the power of negative 34 joules seconds.